Hello, I'm Dr. Fife, and I'm here with a brief lecture for Chapter 4, starting with Section 4.1. Chapter 4 covers solving higher order linear ODEs. So in this brief lecture, we will state the general form of a higher order linear ODE. We'll talk about the difference between linear independence and linear dependence of solutions. And then we'll talk about using the Wronskian to test for linear independence of solutions. So first, the general form of a higher order linear ODE is here shown on the screen. We have a sub n of x, that's some function of x, times the nth derivative of y with respect to x, and then the a sub n minus 1 of x multiplied by the m minus first derivative of y plus going all the way down to a sub 1 of x times y prime plus a sub 0 of x times y equals g of x. So we have all of these functions of x. They really could be anything, and multiplied by some derivative of y. And then, so we have all these y terms, y or y derivative terms, just multiplied by some derivative of x. We should say that a sub n of x cannot be equal to 0. That leading coefficient can never be equal to 0. But in general, this is our definition for a linear ODE, that we have those derivatives multiplied by some function of x, or by a constant, which could be a function of x. So we're going to solve nth order ODEs. Most of our equations are going to be second or third or fourth order equations. They could be higher order as well. And if we have an nth order ODE, we should be able to find n linearly independent solutions. So we're going to talk about linear independence. We need n linearly independent solutions to an nth order homogeneous linear ODE. So the homogeneous, an equation is homogeneous if this g of x is equal to 0. Homogeneous, g of x equals 0. And we're going to start by looking at cases where we have constant coefficients. The constant coefficients, that means that these a sub n of x, a sub m minus 1 of x, and so forth, these are constants. So C1, C2, and so forth. What this is saying is that if y sub 1, y sub 2, all the way to y sub n are solutions, and if they are linearly independent solutions, then we can construct our general solution to the equation by putting those solutions together, multiplying by a constant, and adding. And if, when you add all of those, if you get 0, only when all of those constants are 0, then those solutions, y1, y2, all the way to yn, are linearly independent. Otherwise, they're linearly dependent. So one tool to test for linear dependence is called the Wronskian. The Wronskian is a determinant. It's an n by n determinant. If you have three functions, you're going to have a 3 by 3 determinant, where the first row contains the functions. So those are y sub i's. The second row contains the first derivative, y sub I prime. So y sub 1 prime, y sub 2 prime, and so forth. And then the last row is the n minus first derivative. So if the Wronskian is never equal to 0, then the functions are linearly independent. Otherwise, they're linearly dependent. Here's an example. So we want to find the Wronskian for these two functions, and then we're going to determine if they are linearly independent functions. So my Wronskian, here I have two functions, so I'm going to have a 2 by 2 determinant. My first row just consists of those two functions, e to the x and xe to the x. My second row will contain the first derivative of each of those functions. The derivative of e to the x is e to the x. And the derivative of x e to the x, here we have to use the product rule for derivatives. The derivative of x is 1, so I get 1 times e to the x, and then plus the derivative of e to the x is e to the x, and that gets multiplied by x. So my derivative of x e to the x is e to the x plus e to the x times x. To find the determinant, I would multiply the first diagonal and then subtract off the backward diagonal product. E to the x multiplied by e to the x is e to the 2x. So here I'm going to get e to the 2x plus e to the 2x times x, and then minus, when I multiply the backward diagonal, xe to the x times e to the x is xe to the x, or xe to the 2x. And notice that these terms will cancel, leaving me with e to the 2x. So e to the 2x is never equal to 0. This is not equal to 0. And therefore, y1 equals e to the x, and y2 equals x e to the x are linearly independent. Now, if these are both solutions to the same second order ODE, then the general solution is going to be C1 times e to the x plus C2 times x e to the x. And we'll see that later on. Let's look at the Wronskian for three functions. So here I have three functions. I'm going to have a 3 by 3 determinant. My first row is going to just contain those functions, 1, x, and x squared. My second row will contain the derivative of each of those functions. The derivative of 1 is 0, derivative of x is 1, derivative of x squared is 2x, and then my third row will contain the derivative of my second row. So I'm going to get 0, 0, and 2. There are a couple of ways to find determinants of a 3 by 3 matrix. I usually expand across a row or a column. I'm going to expand across this first row. When you use this expansion method, you start with each element in that first row. So I'm going to start with 1, and then multiply by the determinant that's left, after removing that row and that column. So removing the first row and first column leaves me with those elements in the bottom right, 1, 2x, 0, and 2. And then the next term is going to be a negative. Each place has a sign plus or minus, starting with plus in the upper left. So that second term is going to be a minus. Now I'm at the x. And I'll take away the first row and the middle column. That's going to leave me with the 0, 0 on that first column, lower first column, and it'll leave me with 2x and 2 on that third column. And then we have plus x squared times here, I'm going to take away the first row and last column, and it leaves me with that 0, 1, 0, 0. 0, 1, 0, 0. Notice those signs that I have here in purple, those are only used for these coefficients, for the 1, the negative x, and the x squared. So now I'll calculate this. For that 1, that's just a 1. So here I'm going to get 2 minus 0, that's just 2, minus x times, here I have 0 minus 0, so that drops out. And then on that last determinant, I have x squared, and I have 0 minus 0. And all of this leaves me with the 2. Notice that 2 is not equal to 0, and so y1 equals 1, y2 equals x, y3 equals x squared are linearly independent. Oh, I should have done another example. But as a brief lecture, this is section 4.1. So just a summary, higher order linear ODE requires n linearly independent solutions to form a general solution. If you have an nth order ODE, you need n linearly independent solutions. You can use the Wronskian to test for linear independence, and if the Wronskian is not equal to 0 at some point, then the functions are linearly independent. Okay, so I'm going to end the lecture right here, and then I'll come back with section 4.2.